Greetings. This is Nate's rendition of Homework 10, Problem 1, Part 1, the Poisson process. Within the first order properties, we see the probability mass is equal to P, excuse me, the quantity x to t equal to k, and is equal to e to the minus lambda t to the k over the k factorial. The second order statistical properties begin with the definition for P or the Poisson process as being P to the random variable n, which is the group T1 or the interval T1, T2 is equal to K, and E2 is equal to e to the minus lambda t over the quantity lambda t to the k over the k factorial. The mean, n of t, is equal to the expected value of the random variable x of t, the stochastic process x of t, which is equal to lambda t. The autocorrelation r of the interval t1, t2 is equal to lambda squared T1, T2 plus lambda min T1, T2. The autocovariance is C, T1, T2 is actually equal to lambda min T1, T2. Now, in regard to discussions, what came up is the mean of the Poisson process, lambda t, is a linear function of t. It matches our common sense. The longer time we wait for the expected number of objects, points, buses, whatever, it's just larger. The autocorrelation function contains a term min T1, T2, which comes from the property, originates from the property of independent increments. Okay, that's the end of the first section of part 1. This is a continuation of the overview of the Poisson process. The understandings are several. One, this process utilizes a Poisson random variable with the parameter lambda t to determine the probability of whether k is the number of points is realized in a time interval t. A Taylor series expansion determines the actual probability. 3. This process is often exemplified by the number of calls received by an operator within a specific time period. But other experimental outcomes are doable, such as departures, traffic patterns, inclusive of network routing scenarios, and other locus of points phenomena. 4. At least 2 instances of time must exist. 5. If the time intervals are not overlapping, the associated random variables are deemed, or rather the associated time intervals are deemed independent. The autocorrelation and the autocovariance functions are indifferent to the interval's start and end times. In effect, they sometimes leverage the absolute value. Well, that's what it's meant there. Thank you. This is homework assignment 10, problem 1, part 2, the Poisson increments. The first order properties or probability masses is y of t is equal to n over epsilon. which is equal to e to the minus lambda epsilon, the quantity lambda epsilon to the n over the n factorial. Its second order properties, by definition, are y of t is equal to the random variable x, the quantity t plus epsilon, minus the random variable x of t over the denominator epsilon. The mean, or nt, is equal to the expected value of y of t, which is a lambda. The autocorrelation r of t1, t2 is equal to lambda squared when the absolute value of t1 minus t2, or tau, is greater than epsilon, or it is equal to lambda squared plus the quantity lambda over epsilon minus lambda times t1 minus t2 quantity over epsilon when the absolute value of t1 minus t2 is less than epsilon. The autocovariance C of t1 t2 is equal to 0 when the absolute value of t1 minus t2 is greater than epsilon, or it is equal to lambda over epsilon minus lambda, the quantity t1 minus t2, over epsilon squared when the absolute value of t1 minus t2 is less than epsilon. This is a continuation of part 2 of assignment 10, problem 1, discussions. Well, this Poisson increment process introduces us to define Poisson impulse processes. Actually, it's one way to define them. It is interesting to see that the quantity lambda over epsilon equal to lambda, the absolute value of t1 minus t2 over epsilon squared, is the value at the quantity of the absolute value t1 minus t2 is less than epsilon. That is the expression of the autocorrelation. It's a triangle as reflected in under the examples with an area of lambda which is independent of epsilon. When epsilon goes to 0, the triangle becomes an impulse with area lambda. Now, in regard to our understandings, or my understanding, number 1, the Poisson increment process is driven by two random variables, specifically x of t plus epsilon and x of t, that differ only in the value of epsilon. 2, the denominator epsilon is bounded by the value 0, which invalidates the stochastic process as it approaches 0, since the process is undefined at 0. 3, in computing a autocorrelation and autocovariance, 4 statistical degree levels were utilized and subsequently combined for finalization. And that is the end of problem 1, section 2. Continuation of assignment 10, problem 1, part 3. The discussions are that the process z of t minus lambda has a 0 mean, and its autocorrelation is r t1 t2 equal to lambda delta t1 t2. That is, Z of t minus lambda is white noise. In the real world, there are some shot noises. You note the two examples that are furnished. We may define it as the output of a linear time invariant system with h of t, the impulse response, and as an input to a Poisson impulse process. As noted in one of the lecture notes on page 67. The understandings are that this is a stochastic process. It's the first derivative of another stochastic process, the Poisson process. But as a discrete process, it is asserted specific points would be required to determine the probability masses, and they were not done. Perhaps this could be used as some facet of the limiter, but I am still a little unfamiliar with this particular process. Thank you. This is homework assignment 10, problem 1, part 4, the semi-random telegraph signal. Probability masses, in this case, are x of t equal to 1, which is equal to e to the minus lambda t, lambda e to the minus lambda t plus e to the minus lambda t over 2. In fact, okay, this is also equal, this is the other side of this, where x of t is equal to a minus 1, and that's equal to e to the minus lambda t, e to the lambda t minus e to the lambda t over 2. Okay, the distinctive confusion, and certainly in my talking, is to recognize that there are two points of time that need to be recognized here. The second order properties, the definition P of n is T1, T2 is equal to K, where the probability itself is equal to a minus lambda t to the lambda t to the k over the k factorial, and the fact that x of t is equal to a plus 1 when k is even on the interval 0 to t, or x of t is equal to a minus 1 when k is odd in the interval 0 to t. The mean for the process n of t is equal to the expected value of x of t, which is equal to e to the minus 2 lambda t. Continuation of homework assignment 10, problem 1, part 4. And here we have the autocorrelation of the semi-random telegraph signal. The autocorrelation R of T1, T2 is equal to e to the minus 2 lambda times the absolute value of T1 minus T2. The autocovariance, C, T1, T2 is equal to e to the minus 2 lambda, the absolute value of T1 lambda, the absolute value of T1 minus T2 minus e to the minus 2 lambda times the quantity T1 plus T2. In discussions, P of x of t equal to 1 is not 1/2 because we start with plus 1, and it should be a little higher than the half. And obviously, it deals with how we handle the estimation that's used in the Taylor series. The px of t equals 1 is equal to e to the minus lambda t times e to the lambda t. That's why I may have screwed up before. E to the plus lambda t plus e to the minus lambda t over 2, which is equal to 1 minus e to the 2 lambda t over 2. And we see there where it goes to a half when t goes to infinity, which matches our expectation. The expected value e to the xt is equal to e to the minus 2 lambda t. It goes to 0 when t goes to infinity, which matches our expectation as well. R of t1, t2, the autocorrelation is equal to e to the minus 2 lambda, the absolute value of t1 minus t2. It goes to 0 when t1 minus t2 goes to infinity. That matches our common sense when t1 and t2 are far away. X of t1 and x of t2 are less correlated. In regard to the understandings, which you certainly couldn't tell from the way I talk, number one, since x of 0 is not fixed at 1, this is a semi-random telegraph signal as opposed to the random telegraph signal. 2, this is a member of the Markov family of processes. Thank you very much. This is Nate's rendition of Homework 10, Problem 1, Part 5, the random telegraph signal. Here, the only thing, at this time, the only thing that fits into the window of the mass, that the projection, is that the probability mass of probability of y of t is equal to 1, which is equal to the probability y of t is equal to a minus 1. The random variables have those values, and the probability itself is equal to a half, which is graphically shown, just the typical Poisson type of graph. This is a continuation of the random telegraph signal. Item 5. The second order properties, statistical properties, are the definition y of t is equal to a times the random variable x of t. This is where the probability of a equal to 1 is equal to the probability of a equal to a minus 1, and the probability is 1/2, where x of t is the semi-random telegraph signal. Now the mean n of t of the expected value of y of t is equal to 0. The autocorrelation RT1, T2 is equal to e to the minus 2 lambda, the absolute value of T1 minus T2. The autocovariance C, T1, T2, is equal to e to the minus 2 lambda times the absolute value of T1 minus T2. In terms of some of the discussions regarding this particular process, the probability y of t equal to 1, or rather the random variable equal to 1, and py of t equal to a minus 1 is equal to the probability 1/2. This makes us guess that y of t may be strict sense stationary. However, seeing that its mean is equal to 0 will lead us to believe that it is not. It's weak sense stationary. But let me continue on. Understanding 1, since the semi-random telegraph signal and the random telegraph signal probability masses are quite different. Likewise, is there other marginal statistics? 2, in somewhat of a mathematical distinction between the two, between randomness and certainty, py of t equal to 1, which is equal to the pa x of t equal to 1, which is equal to x of t equal to minus 1, with a equal to 1 plus px of t equal to a minus 1 and a equal to a minus 1 equal to px of t equal to 1, pa equal 1 plus px of t equal to a minus 1, and all this equal to the probability of 1/2. I know I stumbled over something and I can see where perhaps some typos existed, so I will have to look at that before submitting the actual written report. Thank you. This is Nate's rendition of homework assignment 10, problem 1, part 6, the random walk process. Additionally, as you probably may not be able to determine, I laid a lot of this out in a table. And basically, in taking the recording of the table, sometimes the layout doesn't allow itself to transcend a page. So that's why we have so many of these breakups, if you will. But in this particular instance, on the random walk process, the probability mass is that x of t, the random value x of t, is equal to the random value x of nt, big T, is equal to rs, which is equal to n over n plus r divided by 2 times 1 over 2 to the n. This is the continuation of part 6, the random walk. Here its definition with the random variable of n of big T equal to ks minus the quantity n minus ks times s equal to the quantity 2k minus n times s, this random walk definition. The mean nt is equal to an expected value that comes up 0. Its autocorrelation, r of t1, t2, is equal to the expected value of x of t1 times x of t2 by definition, in effect. And it is equal to the expected value of the random variable x of nt times the random variable x of mt, which is discerning something, and is equal to the minimum nm times s squared, which is certainly a function of multiplying these terms out. The auto covariance C of T1, T2 is equal to the expected value of x1 times the expected value of x2, which in turn is equal to e the expected value of x to the quantity n of big T times x times the quantity m of big T, which again is equal to a minimum of nm times the quantity s squared. From the probability masses, we guess that when n goes to infinity, we will have a Gaussian density. The autocorrelation function contains a term min 1, 2, or T1, T2, which was an attempt to type in the items rather than pick up the graphics, but I could not get the subscripts to work, which is why they come up that way, which comes from the property of the independent, not indefinite, independent increments. Random walk is somewhat a very popular approach. While there's a significant reliance on the min function, certainly that's to be expected. It's just a summarization of some of the equational the terms in the equation, reflecting an indifference to the time interval boundaries. Perhaps unpredictability could augment pricing scenarios. Certainly long since used, I've always heard of the random walk, but there's also something called Sholes-Blackshear, which may be more prevalent now. But in our examples, we're dealing with the unpredictability of the outcomes, and they're between a coin flip in one particular scenario, which is reflected in the graph, and then in the notes, there was a reference to a graph in Professor Chen's stochastic notes. So I basically added that to this particular display. Thank you very much. Greetings. This is homework assignment 10, problem 1, part 7, the Wiener process or Brownian motion. We can see that the first order property is the density f of wt is equal to 1 over the square root of 2 pi alpha t times e to the minus w squared over 2 alpha t. The second order properties, the definition, wt is equal to the limit of x of t as t approaches square over x as it approaches a, and a approaches infinity, where x of t is random walk. The mean n of t is equal to the expected value of wt, which is equal to 0. The autocorrelation r t1, t2 is equal to the min of t1, t2 alpha, and the auto variance is c t1, t2, t1, t2 is equal to the min of t1, t2 times alpha. So certainly the autocorrelation and the invariance, the autocorrelation and autocovariance are identical. Okay, to begin the discussion, the Wiener process, Wt, is characterized by the following properties. 1, W, the initial value of W0 is WO is 0 with probability 1. 2, W has independent increments, and W1 plus U minus Wt is independent of Ws as such that S is less than T. For U greater than 0, Item 3, W has Gaussian increments. Wt plus U minus Wt is, and that'll be continued in the next section. Thank you. This is a continuation of homework assignment 10, problem 1, part 7, the Wiener process. And we continued previously where it was stated independent of sigma Ws such that sigma is less than T for U greater than or equal to 0. 3. W has Gaussian increments. W T plus U minus Wt is normally distributed with mean 0 and variance U. W T plus U minus Wt is equivalent to normal from 0 to the interval, the normal interval is 0 to U. Item 4, W has continuous paths with probability 1. 5, W is continuous in T. 6, law of iterative logarithms. I presume this is what this is. Limited sum as T approaches plus infinity of the absolute value of U of T over the square root of 2T log T equals 1. Boy, I haven't seen that in decades. Almost surely. There are lots of good properties. Also limited understanding here, where the Wiener process have a limiting influence to the random walk stochastic process. 2. There is no 2. Alrighty, that's it. Thank you very much. I'll correct that last part on the report.